Welcome to this coding walkthrough. Today, we'll be solving LeetCode problem number 1677, titled Sum of All Subset XOR Totals. In this problem, we'll explore how to calculate the XOR total of all subsets of a given array efficiently. Let's dive in. In this problem, we are given an integer array called nums, and our goal is to calculate the sum of all XOR totals for every subset of this array. First, let's understand what an XOR total is. The XOR total of an array is found by applying the XOR operation to all elements of the array. For instance, if the array is 2, 5, 6, the XOR total is computed as 2 XOR 5 XOR 6, which equals 1. Now, we want to find all possible subsets of the array, calculate the XOR total for each subset, and then return the sum of those XOR totals. One important thing to note is that subsets with the same elements but different indices in the original array are considered distinct. The input to our function will be the nums array, and the output will be a single integer representing the sum of all XOR totals across all subsets. Let's look at the first example. Here, the input array nums is 1, 3. The subsets of this array are the empty subset, the single element subsets 1 and 3, and the full array 1, 3. For each subset, we calculate the XOR total. The empty subset gives an XOR total of 0. The subset 1 has an XOR total of 1, and 3 results in an XOR total of 3. Finally, the subset 1, 3 gives 1 XOR 3, which equals 2. Summing these XOR totals, we get 0 plus 1 plus 3 plus 2 equals 6. Hence, the output for this example is 6. Another example is when nums is 5, 1, 6. The output here is 28, and we'll break this down further in the next section. For the second example with nums equals 5, 1, 6, we calculate the XOR totals for all subsets of the array. Starting with the empty subset, its XOR total is 0. The single element subsets 5, 1, and 6 have XOR totals of 5, 1, and 6, respectively. Next, for subsets with two elements, 5, 1 gives 5 XOR 1 equals 4, 5, 6 gives 5 XOR 6 equals 3, and 1, 6 gives 1 XOR 6 equals 7. Lastly, the full subset, 5, 1, 6, results in 5 XOR 1 XOR 6 equals 2. Adding these values together, the sum of XOR totals is 0 plus 5 plus 1 plus 6 plus 4 plus 3 plus 7 plus 2 equals 28. Similarly, for nums equals 0, 0, 0, all subsets contain only zeros, so every subset's XOR total is 0, and the sum of all XOR totals is also 0. To ensure the solution works for all cases, let's consider the constraints and edge cases. First, the input size is limited to nums.length equals 12, which means there can be up to 2*12 equals 4096 subsets. Additionally, each element in the array can be as large as 10*4. For special cases, if nums contains only one element, the XOR totals will simply be the XOR of 0 from the empty subset and the single element itself. For example, if nums equals 5, the result is 0 plus 5 equals 5. Another edge case is when all elements are zeros, where the XOR total of every subset is 0, resulting in a sum of 0. Efficient computation is vital because iterating through all subsets explicitly would be computationally expensive. Instead, we can leverage properties of the XOR operation, such as commutativity and associativity, to optimize the solution. To solve this problem, the first approach we can consider is the brute force method. The intuition here is to generate all possible subsets of the array nums. For each subset, we calculate the XOR of its elements, and then sum up the XOR values of all these subsets to arrive at the final result. In terms of implementation, we can use a backtracking technique or an iterative method to generate the subsets. Once a subset is formed, we compute the XOR of its elements and accumulate the results. However, this approach comes with significant computational cost. Generating all subsets requires O(2 to the power of n) operations, where n is the size of the input array, and computing the XOR for each subset adds another layer of complexity. On average, subsets have a size of n/2, so the total time complexity becomes O(2 to the power of n*n. This makes the brute force method impractical for larger arrays due to its exponential growth in complexity. While straightforward, it's important to note that this approach is not efficient for larger inputs. To improve upon the brute force method, we can use an optimized approach that leverages recursion. Instead of explicitly generating subsets, we compute the XOR totals directly by exploring the two choices for each element, including it in the current XOR total or excluding it. This recursive strategy eliminates the need to generate subsets, making the process more memory efficient. The key idea here is to define a recursive function that keeps track of the current index in the array and the cumulative XOR values so far. At each step, we make two recursive calls, one where we include the current element in the XOR calculation and another where we exclude it. When the index exceeds the bounds of the array, we return the accumulated XOR value. By summing the results of these recursive calls, we get the total XOR sum for all subsets. While this approach still involves O2 to the power of n recursive calls because each element is considered twice, it is more efficient in terms of memory since we avoid storing intermediate subsets. This makes it a better alternative to the brute force method. Another way to solve this problem is by using bit manipulation, which offers a highly efficient solution. The intuition behind this approach is to recognize that each element in the array contributes to the XOR total of multiple subsets. Specifically, each element appears in exactly half of all subsets, which is 2(n1) subsets, where n is the size of the array. Instead of recursively calculating the XOR totals, we can directly compute the contribution of each element. To implement this, we calculate the total number of subsets an element appears in, which is 2(n1). Then, for each element in the array, we multiply its value by this number and sum up the results to get the final XOR total. This approach has a time complexity of O(n), as we only iterate through the array once, and a space complexity of O(1), since no additional memory is required. While this method is the most efficient, it relies on understanding the mathematical property of XOR contributions, which might not be immediately intuitive for all users. For this problem, the chosen strategy is the recursive XOR calculation approach. This method strikes a balance between simplicity and efficiency. It avoids the memory overhead of explicitly generating subsets, as seen in the brute force method, while still being conceptually straightforward to implement. When comparing the different approaches, the brute force method, though simple, is computationally infeasible for larger inputs due to its O2 to the power of n*n complexity. On the other hand, the bit manipulation approach is the fastest, with a linear time complexity, but it requires a deeper understanding of XOR properties, which might make it less accessible. The recursive approach, while still exponential in time, is more intuitive and easier to grasp, making it a good compromise between readability, maintainability, and efficiency. This is why the recursive strategy is chosen as the ideal solution for this problem, offering a practical way to calculate the XOR totals effectively without being overly complex. To tackle the problem of finding the sum of XOR values of all possible subsets of an array, we can begin with the brute force approach. First, we need to generate all subsets of the given array nums. This can be achieved using backtracking, where each element is either included or excluded to form all possible combinations. For instance, if nums is 1, 2, the subsets would be 1, 2, 1, 2. Once we have the subsets, the next step is to compute the XOR of all elements within each subset. The XOR of an empty subset is 0, and for other subsets, we simply apply the XOR operation across their elements. For example, with 1, 2 as the input, we get the XOR results as 0, 1, 2, 3 for the subsets 1, 2, 1, 2. This process lays the foundation for calculating the total XOR sum by considering all possible subsets. Now that we've computed the XOR values for each subset, the next task is to sum them all up. This involves maintaining a running total and adding each subset's XOR result to it. For example, with subsets 1, 2, 1, 2, from nums equals 1, 2, the total XOR sum is 0 plus 1 plus 2 plus 3 equals 6. Once the sum is complete, we return the final result. While this brute force approach is straightforward, it becomes inefficient as the size of the array increases, due to the exponential growth in the number of subsets. To optimize, we can use a key insight: each number in the array contributes to the XOR sum exactly 2(n1) times, where n is the size of the array. This is because each element appears in exactly half of the total subsets, as the other elements can independently either be included or excluded. Using this insight, we can bypass subset generation entirely by directly calculating the contribution of each number. This involves multiplying each number by 2 and 1 and summing up the results. To implement the optimized approach, we first compute 2 and 1, which represents the number of subsets in which each element contributes to the XOR sum. Then, we iterate through the array, multiplying each element by this factor and accumulating the total sum. Finally, the accumulated sum is returned as the result. This approach is highly efficient because it eliminates the need to generate subsets, reducing the time complexity from O(2 to the power of n) to O(n). The insight that each element contributes to the XOR sum exactly 2 and 1 times is the cornerstone of this optimization. It allows us to perform the computation directly, leveraging the mathematical properties of subsets. Additionally, the space complexity remains constant at O(1), as we only use a few variables for calculations. This makes the optimized approach both time-efficient and space-efficient. Let's walk through an example to see both approaches in action. For the input nums equals 1, 2, 3, the brute force method generates all subsets 1, 2, 3, 1, 2, 1, 3, 2, 3, 1, 2, 3. The XOR results for these subsets are 0, 1, 2, 3, 3, 2, 1, 0, which sum up to 12. In contrast, the optimized approach calculates 2 and 1 equals 2 3 to 1 equals 4 and determines each element's contribution directly. 1 * 4 plus 2 times 4 plus 3 times 4 is equal to 4 plus 8 plus 12 equals 24. The result from the optimized approach is 24, highlighting its efficiency and accuracy. The Python implementation of this method is concise. We compute the multiplier 2 and 1 using a bitwise left shift, then loop through the array to calculate the total XOR sum. This simple yet powerful approach demonstrates how leveraging mathematical insights can significantly enhance algorithm performance. This Python solution implements a recursive approach to solve the problem of calculating the sum of all subset XOR totals for a given list of integers. The function subset XOR sum takes a list nums as input. To solve the problem, we use a helper function backtrack that recursively explores all possible subsets of the array. For each subset, we calculate its XOR total and sum these values. ### line by line explanation. 1. Backtrack function asterisk. This recursive function takes 2 arguments, index, the current position in the list, and current_XOR, the XOR value computed for the subset formed so far. The base case is triggered when index equals the length of nums, meaning all elements have been processed. At this point, the function returns the XOR value of the current subset. 2. Recursive step asterisk. For each element in nums, 2 choices are explored. Include the current element asterisk. The XOR total is updated by XORing current_XOR with nums, index, and the recursion proceeds to the next index. Exclude the current element asterisk. The XOR total remains unchanged, and the recursion proceeds to the next index. The function returns the sum of the results from including and excluding the current element, ensuring that all subsets are considered. 3. Starting the recursion asterisk. The recursion is initiated from the first element, index equals 0, with an initial XOR total of 0. ### complexity. Time complexity asterisk. Each element in nums has 2 choices, include or exclude, leading to 2 to the power of n subsets. Therefore, the time complexity is O(2 to the power of n). Space complexity asterisk. The recursion depth is at most n, so the space complexity is O(n). This approach is efficient for small to moderate input sizes and leverages the power of recursion to systematically compute XOR totals for all subsets. This is the Java implementation of LeetCode problem number 1677, sum of all subset XOR totals. The logic mirrors the Python version, using recursion to compute the XOR totals of all subsets. The backtrack method handles the recursive traversal, with base and recursive cases. Key differences include the use of Java's type declarations and method signatures. To solve the problem, we start with an example where nums is 1, 2. The process begins with an initial call to backtrack at index 0 and a current XOR value of 0. At this stage, we examine nums 0, which is 1. We have two options: include it in the subset or exclude it. If we include nums 0, we compute the new XOR as 0 XOR 1, which equals 1, and make a recursive call to backtrack with index increment to 1 and the updated XOR value. If we exclude nums 0, the XOR remains 0, and we proceed with backtrack at index 1 but keep the XOR unchanged. Next, we process nums 1, which is 2. For the backtrack call with an XOR of 1, including nums 1, updates the XOR to 1 XOR 2, giving 3, and we make a recursive call with index 2. Excluding nums 1 keeps the XOR at 1, and we continue to the next step. Similarly, for the branch where nums 0 was excluded, including nums 1 results in a new XOR of 0 XOR 2, which is 2, while excluding it keeps the XOR at 0. This step explores all possible subsets formed by including or excluding each number in the input array. Now, at index 2, we hit the base case of our recursion. Here, the current XOR value is returned as it represents the XOR total for a specific subset. For instance, the call backtrack 2, 3 returns 3, backtrack 2, 1 returns 1, backtrack 2, 2 returns 2, and backtrack 2, 0 returns 0. These values correspond to the XOR totals of subsets formed in earlier steps. Once these results are returned, we sum them up to get the total XOR value for each branch of the recursion. From the path that included nums 0, the sum is 3 plus 1, which equals 4. From the path that excluded nums 0, the sum is 2 plus 0, which equals 2. Finally, adding these two totals gives the overall result for the input, 1, 2, which is 4 plus 2, resulting in a final output of 6. This demonstrates how recursion systematically calculates and combines XOR values for all possible subsets. Let's consider another example with nums equal to 5, 1, 6. The process begins with an initial call to backtrack at index 0 and a current XOR of 0. The first number, nums 0, is 5. If we include it, the XOR updates to 0 XOR 5, which is 5, and we proceed with backtrack at index 1. If we exclude it, the XOR remains 0, and we move to index 1. Now we process nums 1, which is 1. For the branch where nums 0 was included, including nums 1 updates the XOR to 5 XOR 1, which equals 4. Excluding nums 1 keeps the XOR at 5. For the branch where nums 0 was excluded, including nums 1 updates the XOR to 0 XOR 1, which equals 1, while excluding it keeps the XOR at 0. This step outlines how the recursion explores all combinations of including or excluding the first two numbers in the input array. Next, we process the last number, nums 2, which is 6. At this stage, we evaluate all possible subsets formed in the previous steps. For each branch of the recursion, we have two options: include nums 2, which updates the XOR by performing an XOR operation with 6, or exclude nums 2, which keeps the XOR unchanged. After processing nums 2 across all branches, we reach the base case at index 3, where we return the current XOR value for each subset. These returned values represent XOR totals for all possible subsets of the input array. Finally, we sum the results from all paths to compute the overall XOR total for the input, 5, 1, 6. Combining these values gives us a final output of 28, illustrating the systematic computation of XOR totals for larger arrays. Now, let's look at a larger example where nums is 3, 4, 5, 6. Here, the recursion follows the same pattern. Starting with nums 0, we explore both options, including or excluding it, resulting in XOR values of 3 and 0, respectively. For each state, we proceed to nums 1, again branching into include and exclude paths, and continue this process recursively for all elements in the array. At the base case, we return the XOR values for all individual subsets. Summing these results gives the final output for the input, 3, 4, 5, 6, which is 480. This example emphasizes key observations about the approach. The recursion systematically explores all subsets by including or excluding each element. The XOR operation is used to compute the current XOR for each subset, and the base case returns the XOR for individual subsets. Finally, the overall result is obtained by summing up the XOR values of all subsets. Here, we're analyzing the time complexity of the solution. which employs a backtracking approach to compute the XOR totals for all subsets of the input array nums. The size of the array is denoted as n. The recursive structure of the solution involves making a binary decision at each element in nums, either include the current element by performing an XOR operation with current_XOR and recursing, or exclude it and recurse without modification. This binary decision process forms a decision tree with 2n leaf nodes, corresponding to the 2n subsets of the array. Each recursive call involves a constant amount of work, including checking the base case, performing the XOR operation, and making 2 recursive calls. Combining these observations, we conclude that the recursion explores all subsets, and since the operations per subset are constant, the overall time complexity is O(2 to the power of n). Now, looking at the space complexity, the main factor is the recursive call stack. The depth of the recursion tree corresponds to the number of elements in nums, which is n. This means that at most n recursive calls can be active at any time, resulting in a space requirement of O(n) for the call stack. Furthermore, the solution does not use any additional data structures that scale with the size of nums. The only extra space used is for storing function arguments like index and current_XOR, which are constant for each call and do not depend on n. Therefore, the overall space complexity of this approach is O(n). When comparing this backtracking solution to a brute force approach, we see significant differences in space utilization. A brute force method would explicitly generate all 2n subsets, compute their XOR totals, and sum them. This would incur a time complexity of O(2 to the power of n) for generating subsets and an additional O(k) per subset for XOR computation, where k is the average subset size, approximately n/2. This leads to an overall time complexity of O(n*2 to the power of n). The space complexity in this case would be O(2 to the power of n*n) to store the generated subsets. In contrast, the backtracking solution eliminates the need to store subsets, reducing the space complexity to O(n). While the time complexity remains O(2 to the power of n), the optimized approach avoids the overhead of subset creation and relies on efficient XOR computations during recursion. Both the best and worst cases involve exploring all 2n subsets, making the time and space complexities consistent in all scenarios. To summarize, the backtracking solution achieves a time complexity of O(2 to the power of n) due to the need to explore all subsets of the input array. The space complexity is O(n), attributed to the maximum depth of the recursive call stack. This approach is asymptotically optimal for the problem, as it avoids the extra overhead of explicitly generating and storing subsets that would occur in a brute force approach. By leveraging efficient recursion and constant time XOR operations, the solution balances performance and resource usage effectively. When approaching problems involving subsets or recursion, there are a few common mistakes that can trip you up. First, forgetting to handle base cases, such as empty subsets or an empty input array, can lead to runtime errors or invalid results. For example, your solution might assume there's at least one element and attempt operations on a none value or out-of-bound indices. Next, failing to optimize brute force solutions is another frequent issue, especially when working with XOR operations. Remember that properties like a XOR A equals 0 can simplify calculations significantly. Another mistake is incorrectly generating subsets. Since the number of subsets for an array is 2n, a small error in loop control can result in incomplete subsets, leading to incorrect outputs. Lastly, for languages like Java or C++, improper handling of integer overflow during XOR computations or summation can introduce subtle bugs that are hard to debug. Being mindful of these pitfalls can save you a lot of time and effort. Now, another common challenge is misunderstanding XOR properties. XOR has specific rules, such as being commutative and associative, that can simplify your logic. For instance, knowing that a XOR A equals 0 and a XOR 0 equals A helps eliminate unnecessary calculations. Misapplying these rules often leads to overly complex or incorrect solutions. Speaking of XOR, it's crucial to be comfortable with bitwise operations. Many XOR-related problems rely on manipulating numbers at the binary level, so practicing bit manipulation can give you a significant advantage. Additionally, for problems involving subsets, bit masking is a powerful technique. It represents subsets efficiently and avoids the need for nested loops. As a general tip during interviews, always clarify the problem scope. If constraints allow for small input sizes, brute force approaches may be acceptable, otherwise, optimizations are key. Lastly, always test your solution with edge cases, such as empty arrays, single-element arrays, or arrays with identical elements, to ensure robustness. To deepen your understanding, it's helpful to explore related problems. For example, LeetCode 1863 also focuses on the sum of all subset XOR totals and can provide additional practice with similar concepts. LeetCode 784, which involves letter case permutation, is another great example of subset generation in a different context. Problems like LeetCode 90, which deals with subsets while handling duplicates, or LeetCode 78, a classic subset generation problem, are also worth studying. In terms of approaches, brute force methods involve generating all possible subsets and calculating their XOR totals. While this is simple to implement, its exponential time complexity of O2 to the power of n*n makes it impractical for larger input sizes. An alternative is to use bit masking for subset generation, which is more structured and avoids recursion. Although it still requires O2 to the power of n time, it can be more efficient and easier to debug. Finally, one of the most effective approaches is leveraging optimized XOR computation. This involves using mathematical patterns or XOR properties to calculate results without explicitly generating all subsets. This method often requires a deeper understanding of the problem but can drastically reduce time complexity in certain scenarios. While it may take some time to develop the insight needed to apply this strategy, the trade-off is a significant improvement in efficiency, making it a powerful tool for tackling XOR-related problems. Great job! To recap, we solved the problem using a brute force approach while discussing XOR properties and subset generation. Remember, practicing problems like this helps you build a strong foundation in combinatorics and bit manipulation. If you enjoyed this walkthrough, be sure to like, subscribe, and share. See you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!